These dots are the solutions of polynomials. Aside from looking pretty, they illustrate polynomials' intrinsic complexity. Complexity suggesting that there is no simple formula to express their solutions. For linear, quadratic, cubic, and quartic polynomials, the formulas which yield their solutions are increasingly complex. But the complexity of behavior that polynomials exhibit grows faster than algebraic formulas are able to express. Today, we'll discover how permutational symmetries of solutions tell us about their polynomials and solve the mystery of the missing quintic formula. This graph shows the relationship between a cubic polynomial's coefficients and its solutions. Polynomials have a standard form where each term has an associated coefficient. They're drawn on the graph here. But we want to find its solutions, the values of x for which the whole thing equals 0. We can move a solution and see its effect on the coefficients, and we can move a coefficient yielding some effect on the solutions. The polynomial lives in the complex plane, home to numbers like I and 2 minus I. For each pixel on the screen, we can pass that complex number into the polynomial and see what comes out. We color the input point depending on where the output lands. The brightness shows how far it is from the origin, meaning that the white areas are solutions of the polynomial. The color shows the angle of the output. So, for example, pink means above the origin, and green means below it. Doing this for every complex number on the plane, we can graph our polynomial. You might ask, what's all this complex number business? Why leave the familiar land of the real numbers? In turn, I would ask you, who needs decimals or negatives either? Imagine there's nothing but natural numbers. 0, 1, 2, 3, sitting happily on the right side of the number line. In such a world, there's a big problem. There are equations with no solution, like 2x plus 4 equals 0. We can write this equation, since 2, 4, and 0 are in our number system. But there's nothing we can write here for x that would make this equation come true. Let's plot this polynomial. The coefficients land on numbers in our number system, but the solution to the equation is -2, which isn't one of them. To solve this, we need to invent -2. And furthermore, I can place the coefficients on other values, which force us to invent all the other negatives. Sadly, our number system is still lacking. This equation, 2x plus 1 equals 0, has the same problem. Our coefficients lie on existing numbers, but the solution lands outside of our number system. So it looks like we need fractions too. Heck, let's just add all decimals. We get a nice continuum of numbers. Surely our number system is finally complete. Well then, what about this equation? No real number squared gives us -1. And you can see it too. None of the solutions are on the number line. Just like before, our number line must be missing something. Let's call these solutions I and -I, and add 2i, -2i, and so on, which, combined with the real numbers, forms the complex plane. Up until now, we've been playing whack-a-mole. You invent numbers, and I make an equation that can't be solved without even more numbers. But that game ends here. Wherever we put the coefficients inside the complex plane, the solutions may move around, but they don't jump out of the number system like they did before. What happens on the complex plane stays on the complex plane. This is so important that it's called the fundamental theorem of algebra. Our graph shows us something else too. The number of solutions never changes either. We're looking at a quadratic polynomial. The highest exponent is 2, so there's 2 solutions. With a cubic polynomial, there's 3 solutions. Well, unless we intentionally scrunch them on top of each other, but that's cheating. We call that a solution of multiplicity 2. It counts as 2 normal solutions. You can actually identify the solutions and multiplicities from the graph. Tracing around this normal solution, we see red, then green, then blue. We make a spin around the color wheel. Tracing around the multiplicity 2 solution, we see red, green, blue, then red, green, blue again. The color wheel is duplicated. The degree of the polynomial always matches the number of solutions, as long as we account for their multiplicities. Another way of saying this is that there's always exactly one more coefficient than the number of solutions. But how do they relate to each other? Given the coefficients, how do we know where the solutions should be? It's obvious since I'm plotting the graph for you. But if I give you A, B, and C numerically, how do you find solutions 1 and 2? Before I spoil this problem, let me illustrate its complexities. Let's take the simplest case imaginable, a polynomial with coefficients that are all 1 or -1. There's a few different options of which are 1s and which are -1s. With a quadratic polynomial, there's exactly 8 options. Plotting all of their solutions at the same time, we get this shape. Cranking it up to degree 3, degree 4, and even higher. We were letting the coefficients be either 1 or -1. But what happens if we change those options? As we zoom into these point clouds, there are shapes resembling the dragon curve. That's the same shape that you get by folding up a strip of paper and letting it spring out. The point is, the function mapping coefficients to solutions isn't simple. It must have a bit of magic to it. Even with just 1 and -1 as coefficients, we find ourselves in a zoo of emergent complexity. What can we say about the process which maps coefficients to solutions? Let's start off easy, with polynomials whose highest exponent is 1. With such a linear polynomial, there's only one solution. This case is super easy. To solve ax plus b equals 0, we can just use algebra. But what happens when we go up a degree? Jumping up to a polynomial with highest exponent 2, there's a certain formula you might have learned in school. But pretend you didn't for a moment. 'Cause something starts getting weird in the quadratic case. You see, coefficients and solutions are structurally very different. Looking at the polynomial, if we switch b and c here, we don't have the same function anymore. Notice how the solutions aren't in the same place after I swap the coefficients. The coefficients are an ordered list. They're not interchangeable. The solutions, on the other hand, don't have a particular order to them. In the factored form of the polynomial, we can rearrange as we please, since it doesn't matter what order we multiply the terms. Swapping the solutions with each other, the coefficients go right back to where they started. The coefficients are distinct from each other, but the solutions aren't. This has some bizarre implications. First and foremost, there's no function that takes the coefficients and gives out one solution and is continuous. Here's why. Assume we do have a continuous function that takes in a, b, and c, and it gives us this solution. As we saw before, we can swap the solutions and the coefficients will return to their starting position. But our continuous function gives us a different solution now. Given this same a, b, and c, first it gave us this solution, but then it gave us that solution. That's a contradiction. The function must not be continuous. We could handle this by accepting a function which is discontinuous, like this. Or alternatively, we could consider the two solutions together as a pair and give up on selecting a single one of them. And that means a quadratic formula can't be written with just basic arithmetic. Even if we use other functions, such as sines, cosines, and exponentials, they're continuous and single-valued, so they can't track a solution of the quadratic. What about the quadratic formula? It has this plus or minus square rooty stuff going on. So what makes a square root different from those other functions? We usually say things like, the square root of 4 is 2, but what we're asking to begin with is, what are the solutions of x squared equals 4? Plotting that equation, we of course see the result 2, as well as the negative square root, negative 2. By convention, we define the square root to be positive. But what about the square root of negative 1? We define I as being precisely that. But negative I works too. It goes deeper than that though. Watch as I move the coefficients of the polynomial along the real number line. With real-valued coefficients, the solutions are always vertically symmetrical. So any definition for I written using the real numbers must simultaneously include negative I. They're algebraically indistinguishable, so which gets to be the square root of negative 1 is a matter of mere notation. If we do define the square root function with such an arbitrary choice, its graph is discontinuous like this. We can change our arbitrary choice, and that yucky discontinuity starts to move around. In other words, there's not just one square root function, but a whole class of them depending on that choice. But discontinuities suck. With a bit of change in perspective, we might be able to eliminate it. We can imagine visualizing this function as jutting out of the complex plane to highlight the discontinuity. This is what it looks like if I change that arbitrary choice like before. Notice how we can extend this surface continuously until it meets itself. This is called a Riemann surface. Now that our surface has no sharp edges, we can make our square root function continuous on it. Here's the complex plane. Picking some complex number, we can evaluate the square root by seeing where it intersects with the two sheets. And we can even track it continuously as we move around. This should hopefully make the predicament clear. We're either stuck with a discontinuous square root, which returns a single value, or a continuous square root function, which returns two that are always opposite each other. And this makes sense. As we saw before, either our formula cannot transform continuously, Or otherwise we have to yield both solutions without distinguishing between them to achieve continuity. We've shown that other functions alone can't solve quadratics, but why can square roots? Remember, I can grab coefficients and make a loop which switches the two solutions. Now watch as I make a loop in the input value of the square root function. The solutions exchange places. Let me artificially stretch out that surface so it's clear what's going on. The behavior is just like our polynomial solutions. A loop of the input yields a swap of the two outputs. So, a square root is just the right ingredient to make a quadratic formula. Cubic polynomials are next. If there's a cubic formula, it also can't be written with simple operators, avoiding square roots. The same argument still applies. If I swap two solutions, the coefficients go back to where they started. It turns out, though, that you need more powerful tools than just square roots to solve cubics. First of all, a square root yields 2 values, but we need a function that gives 3. In that case, how about a cube root? The associated Riemann surface has 3 sheets, and the cube root function is continuous on it. Stretching this manifold out so it's easy to see, we can cycle the 3 roots like this, and we can move some coefficients to yield the same behavior on the solutions. That's a good sign, right? Well, not so fast. As we already saw, we can also swap two solutions on the polynomial. But the cube root is only capable of cycling all 3. Maybe we need a square root too, just to permit these swaps like before? To make matters worse, I'm going to pick up those same coefficients again. And this time make a very special sequence of for loops. First, we move them in a way that swaps the left 2 solutions in a clockwise rotation. Then we swap the right 2 clockwise. Now swap the first 2 backwards, and unswap the right 2 backwards. We did 2 things, then undid them both. But watch what happens if I label the solutions this time. The solutions changed places, even though each loop we did was later undone. This special way of cycling objects is called a commutator. But watch what happens if we make commutator loops on the input of the cube root function. Loop, loop, back, back. The solutions return to where they started. Let's try a different commutator on the square root. No matter what commutator the input follows, or which root we try it on, each output always spins back to where it was before the commutator. In general, the roots do a cycle whenever our loop circles around the origin, and don't do anything at all otherwise. But the commutator unwinds any accumulated rotation around the origin in the second half when we're undoing the first 2 moves. The cubic polynomial can therefore express permutations that the square root and cube root are unable to emulate. What kind of operator could be more expressive? Imagine a pole which you need to circle around to cause the outputs to cycle. We're going to use it to construct a machine that has the same behavior as our cubic polynomial. Let's take our square root function's output, and use that as the input of this cube root. This still isn't enough to implement a functional commutator, because we're just accumulating and dissipating rotation between the 2 halves of the commutator. But here's the trick. We skew the square root and cube root functions away from each other like this. Now the 2 poles don't line up anymore. Ready for the commutator? Pay attention to the 3 outputs here. Loop, loop, undo, undo. The 3 outputs did a cycle. Let's try that again. This time, watch the bar tying them together. 1, 2, undo, undo. See how it only went around the bottom pole once? Only going around once mean that the outputs cycle without later being undone. This means, in order to support commutator cycles, we need to use a root as input to another root, along with the term added to skew their two poles apart. And sure enough, this is exactly the tool used in the cubic formula. Quartics have only a slightly harder trick up their sleeve. Watch me do a nested commutator on the solutions. Here's the first commutator. Here's the second. Here's the first one getting undone. And here's the second one getting undone. This nested commutator has scrambled up the roots, just like a single commutator scrambled up the three roots of a cubic. They started like this. If we do any nested commutator on the machine we built earlier, everything goes back to where it started. The workaround is comically simple. Any guesses? Just add another root to the chain. This trend continues inductively. Each time we add a root, we can support another level of nested commutators. With one square root operator, we can represent a single swap on two solutions. With two nested root operators, we can represent a simple commutator on three solutions. With three nested root operators, we can represent a commutator of commutators on four solutions. And so on successively. So why can't we represent actions on quintic polynomials' 5 solutions just by adding another root? Here's the key to the proof, the source of the impossibility. With two objects, we can make a single swap to leave them scrambled. A commutator doesn't really make sense here because there's only one swap to choose from. With three objects, there are commutators which leave them scrambled. But any commutator of commutators does nothing. With four objects, there are commutators of commutators which leave them scrambled. But triply nested commutators do not. But once you have 5 objects, there's a trick. We can take a cycle of 3 like this, and call it A. And another cycle of 3 like this, called B. That's 2 3 cycles, and they only intersect in the center. Now, I'm going to make a doubly nested commutator with A and B. Start with A, B, A backwards, B backwards. Now A backwards, B backwards, A, B. Now undo the first commutator, and undo the second. See what the final result is? Our double commutator simply did A. If we instead order our supercommutator in reverse, all we did was B. From doing doubly nested commutators, we were able to perfectly recover the starting elements. And that means that we can nest those double commutators once again, giving us 4th order commutators, and 6th order commutators, and 8th order commutators, arbitrarily deep nested commutators which are still scrambled. So, tying it all together, for every extra level of commutator, we need one more radical to express the solution. The quadratic polynomial can be scrambled by a single swap. Cubic polynomials can be scrambled by a single commutator of their 3 solutions. The quartic is scrambled by the doubly nested commutator. But as we just saw, the quintic can be scrambled by not just a 3rd order commutator, but also a 4th order commutator, a 5th order commutator, and so on. No finite amount of nested roots will ever be enough. With any finite number of nested square roots, cube roots, you name it, there's always a deeper commutator of 5 solutions we simply cannot express. So there you have it. There's no algebraic formula which solves quintic polynomials or higher. Hopefully that provides some intuition for why polynomial solutions appear so beautiful and intricate. I wanted to make an interactive demo that you could use to explore these fractals yourself, but HTML and CSS aren't my forte, so I used Lovable to make one. To make the page, I just described that I wanted a visualizer for fractals made of solutions of polynomials with certain legal coefficients, and it spit out a working interactive demo on the spot. You can visit the link in the description to play with the parameters yourself. I challenge you to use the demo to drag around the coefficients and try to find ways to swap different roots among themselves. It was extremely quick to make. Lovable made it so easy to play with different options and customize the visualizer. For example, I wondered what would happen if we allowed for 3 legal coefficients instead of just 2. All I had to do was ask. Quickly prototyping alternative designs is easy as cake. I've wondered about making a store to sell 2-swap t-shirts, mugs, posters, and stickers. Just to get a feel for what it might look like, I used Lovable to quickly generate a prototype store. It immediately made a working, beautiful online storefront using the channel art that I provided. It even generated some stand-in demo photos of merchandise. All I had to do was ask. Lovable helps you easily create prototypes and internal tools, as well as fully functional apps, websites, and online stores. And best of all, it's free to try. Go to lovable.dev to start building today, and use my code 2swapyt20 for 20% off. Thanks to Lovable for sponsoring this video.